In this section, we're going to look at bias when you're graphing. There's a number of ways that you can distort a graph to make it look like it's saying something that's different than it really is saying. So you can draw the graph in a way that makes the way people interpret it not exactly accurate. And sometimes this is done intentionally to confuse. So you can either start, these are just 4 techniques, and we're going to kind of look at some examples to see where they come up. You can start the scale. So if you have a graph that looks like this, you can have one of those little line breaks where the scale doesn't start at 0, it starts somewhere else. Let's say it goes from 0 and then it goes up to 50, 51, 52, something like that. That can be one way of distorting a graph that can confuse people. Another thing that could happen is you could use intervals that are not evenly spaced. So imagine another graph here where you have 1, 2, 3, 7. Well, what? So if you had some kind of graph like that where it was not evenly spaced, that could definitely confuse someone or mislead someone. You can distort using inappropriate area, I should say AREA, area, or volume models. So, and that's an example we're going to look at in a second, where you make something that maybe is twice as tall look like it's 4 times as large, or maybe even 8 times as large, based on the way you draw the picture. They can also be distorted by using percentages when the actual numbers would be more helpful. So sometimes percentages can be a little bit misleading, especially when you have small numbers. So let's look at this example. How many times longer does the Extra Life battery last than this brand X battery? And if we look for the number inside, this one says 200 hours and this one says 100 hours. So the Extra Life battery is 2 times longer. 200 is twice as much as 100. Part B says, if the length, width, and height of the bar for Extra Life battery are each twice as great as the corresponding measure of the bar for brand X, how do the volumes compare? So what it's saying here is, if this line, the height, is twice as long as this, but then this line, you double it to get to this one, going back, and you also take this front side length and you would cut that in half when going over here. So every one of these going from this to this would be doubled. And when you do volume, you do length times width times height. So length times width times height. And if the length doubles and the width doubles and the height doubles, 2 times 2 times 2 would be 8 times as big. So why does the graph give a misleading impression of the comparative lifespans of the 2 brands of battery? Well, this one here has twice as much life as this one, but this picture makes it look like it actually is 8 times as much life. The picture of this battery is 8 times as big as the picture of this battery. So that's why it can be very misleading to use volume, to use a 3D shape like this where everything doubled, because it changes the ratio. Instead of being twice as big, now it looks 8 times as big. So these 2 right here is your reason. Let's go to the next one. We have 2 graphs. In the graph on the left, which bar is twice as long as the bar for 1960? And we're looking at the number of women in the U.S. workforce and the number of workers in the millions. So in the one on the left, we have the bar for 1960, and that goes up to about 2 million, and twice as high as that, so this is 2 notches high, twice as high as that would be this one, the 1980 bar. So which one is twice as long? 1980. And the graph on the right, which bar is twice as long as the 1960 bar? Well, the 1960 bar on this graph only goes about 1 full level. And so if you go 2 levels up, it looks like the 1970 bar is almost twice as big. So 1970. In which year was the number of women employed about twice as great as the number employed in 1960? Well, let's look at the actual numbers now. So, number of women employed in 1960 was about 2 million, and so double that should be about 4. So when was it 4? 4 was in 1980. And if we look at this graph here, this is just over 2, so it's about 2 over on this graph, and we double that and get 4. And this graph also confirms that in 1980 was the year when the number of women doubled. So which graph gives an accurate representation of the data? Well, graph A, the bars were twice as tall when the data got twice as much, so that would be pretty accurate. This graph on the right here, when we doubled this, it looks like it almost tripled. So it looks like the bars are a little bit misleading. So we're going to say the accurate one is the accurate one is the left. And why is this one misleading? If you look down at the bottom here, where does it start? It starts at 1. This one starts at 0. So the reason that I would put for it to be misleading is does not start at 0. So does not start at 0. And then part E, explain why proponents of governmental funding of daycare centers might choose the graph on the right to support their position to increase funding. Well, if you're trying to get more daycare centers, then you probably want to show that more women are working than before. And this graph, if it looks like since 1960 the number of women in the workforce has far more than tripled, it's gone up almost 4 or 5 times. Whereas this graph here, maybe 2 to 3 times as many women are in the workforce. So this one looks like it's going up faster than this one does. So if you're trying to say, look at the number of women are just rapidly growing, we need more funding for these daycare centers because so many women aren't staying at home, they're working now, then you would probably want to use that one on the right. So I would say, for my reason, looks like it is increasing faster. Going down to this last example here, a school that gives the MCA test and receives a less than favorable result. They choose to represent their scores in a way that will look better than they actually are. In their district, 40% of the student body met the state standards, so 40% passed and 60% failed. In Excel, you can create a 3D pie chart and kind of rotate the image around so that it will look a lot better. And if you see here, this graph, clearly more than half of it is failing. But if you were to rotate it so that this gray side, the failing or the passing side, was up near the front, and then you were to tilt the graph where the front edge became a lot bigger, you can see in this after graph here, most of the picture, the vast majority of the picture, looks like they passed. Only this little tiny sliver of red back here suggests that anyone failed. And this is something that Mr. Warnicki actually saw when he was visiting a school. He actually saw someone do this to a graph of their MCA data. So this is something that actually happens, how people can distort data to make it look better than it is. So you have to be very careful when you're presenting things in a 3D format like this. And that's misleading graphs.